So now we are going to derive the ideal gas law. But before we derive the ideal gas law, we need to talk about the last named mathematical law governing the properties of gases, and that's Avogadro's law, which states that equal volumes of different gases at the same pressure and temperature will contain the same number of moles of gas. So the number of moles of gas is also related to volume. And volume is directly proportional to the number of moles of gas. Just like in Charles's law, volume was directly proportional to the temperature, volume is directly proportional to the number of moles of gas. So Avogadro's law can be expressed mathematically similar to how Charles's law was expressed. V1 over N1 equals V2 over N2, where N is the number of moles of gas under the two different conditions. So this should make sense. The more moles of gas you have, the larger the volume they will occupy. This is a direct relationship. The greater the volume, the more moles of gas. So if we take Avogadro's law and combine it with Boyle's law and Charles's law, so we put all of those laws together, we can come up with the ideal gas law. So just to remind you, we had Boyle's law, which is P1V1 equals P2V2. That's Boyle's law. We had Charles's law, which is V1 over T1 equals V2 over T2. And now we have Avogadro's law, which is V1 over N1 equals V2 over N2, where N is the number of moles of gas. So if you combine all of those, you can get an ultimate combined gas law of P1 V1 over N1 T1 equals P2 V2 over N2 T2. Say that 5 times fast. P1 V1 over N1 T1 equals P2 V2 over N2, T2, not V2, N2 T2. Okay, that's combining Boyle's law, Charles's law, and Avogadro's law together. Now, let's take one side of the equation, let's say this side of the equation, and let's set this to a fixed set of conditions. And that fixed group of conditions is going to be defined as R. So I'm going to call that R. P1V1 over N1T1 equals R. That fixed set of conditions, R, refers to standard temperature and pressure. So R refers to conditions at STP, standard temperature and pressure. So we need to define what those are. Standard temperature and pressure is defined as a temperature of 0 degrees Celsius. Of course, we want to use Kelvin when we're using gas laws. So adding 273 to that means 273 Kelvin. That's standard temperature. The standard pressure is 1 atmosphere. Now, at standard temperature and pressure, so at STP, 1 mole of any gas, does not matter the identity of the gas, could be xenon, could be neon, could be chlorine, 1 mole of any gas occupies a volume of 22.414 liters. So this is not part of STP because it's a volume, but it just comes out of that STP definition. So if I plug all of those in for R, I can define R as PV over NT for 1 mole of gas. So I have 1 atmosphere times 22.414 liters of volume over 1 mole of gas times 273 Kelvin. And that gives me a value for R that is 0.08206 liter atmospheres per mole Kelvin. This R value is also known as the gas constant. So the gas constant R. And you will find yourself using this quite a lot in this chapter. So let's take this equation right here and rearrange it. So I'm going to put RAR. Let's rearrange that equation. R equals PV over NT. I'm just going to multiply both sides by PV to get PV equals nRT. Okay, so even though I kind of wrote that in the margin here, it is extremely important. This is the ideal gas law. And when we're using the ideal gas law, the R value that we plug in is 0.08206 liter atmospheres per mole Kelvin. You always want your temperature in Kelvin. N is the number of moles of gas. Pressure you want in atmospheres, and volume you want in liters. So let's do some sample exercises with the ideal gas law. First example, a cylinder of xenon gas, xenon is a noble gas, contains 50 liters of xenon at 1,000 atmospheres of pressure at room temperature, 25 degrees Celsius. How many moles of xenon are there? So a cylinder of xenon is highly pressurized. So that's why the pressure is an enormous value here, a pressure of 1,000 atmospheres. So we need to figure out how many moles of xenon there are. So let's rearrange the ideal gas law to solve for N, the number of moles of gas. Rearranging the ideal gas law, N is going to be equal to PV over RT. And I have 1,000 atmospheres of pressure. I have 50 liters as my volume. The gas constant is 0.08206 liter atmospheres per mole Kelvin. And the temperature, 25 degrees, must be converted to Kelvin. Okay, so I add 273, and that's going to give me 298 Kelvin. Okay, so again, make sure that your temperatures are always in Kelvin. Okay, and the reason is you need to be able to cancel with the units of the gas constant. So the moles will flip to the top, and I'll get a number of moles of xenon gas as, 7.63 times 10 to the negative 3 moles. Okay, this is the number of moles of xenon gas in that cylinder. I lied. I thought that looked low. I'm looking at the answer for the next one. Okay, so if you do all of that arithmetic, you should actually get something much larger, 2,040 moles of xenon there. That's more plausible for a cylinder of xenon. Okay, so now let's make it a little bit more complicated with the next example. A 0.939 gram sample, we don't know what it is yet, is vaporized in a 235 milliliter flask at 99.2 degrees Celsius and 0.992 atmospheres, so almost atmospheric pressure. What is the molecular weight of that compound? So here we can actually exploit the ideal gas law to figure out the molecular weight of a mystery compound. Once again, we can use the same relationship that we used in the previous problem to solve for the number of moles of gas. So we can rearrange the ideal gas law to solve for N. N equals PV over RT. Now let's plug in the variables that we have here. We have 0.992 atmospheres for the pressure and 0.235 liters for the volume. So remember, you always need to convert your volumes to liters. So here we're going to convert those milliliters to liters. And the reason, of course, is that the gas constant has units of liter atmospheres per mole Kelvin. So the units of volume need to match so that I can cancel them. Okay. Finally, I need the temperature. So 99.2, I need to add 273 to that because I need to make sure it's in Kelvin. So that's 372.2 Kelvin. Okay, always put your temperature in Kelvin because, 372. I don't know if you can read my writing. Let me write that a little bit neater. 372.2 Kelvin. And of course, I need to cancel those kelvins. So the moles flip to the top. And now I have 7.63 times 10 to the negative 3 moles of this mystery gas. So if you look back at the problem, those moles, those 7.63 times 10 to the minus 3 moles, weigh 0.939 grams. So I can figure out the molecular weight in grams per mole by putting the grams over the moles. 0.939 grams over 7.63 times 10 to the minus 3 moles. Remember, molecular weight is in grams per mole. So this gives me a molecular weight for that mystery compound of 123 grams per mole. So there I exploited the ideal gas law to figure out a molecular weight. Let's do one more example. What volume of oxygen gas at 20 degrees Celsius and 750 torr is produced from the decomposition of 1 gram of KClO3 according to this balanced chemical equation? So I have the solid decomposing under heat. This little triangle here represents heat. So it's decomposing under heat to make solid potassium chloride and oxygen gas. So I want to figure out how much oxygen gas is being produced. So can I exploit the ideal gas law to solve this problem? PV equals nRT. Well, I have the pressure. The gas constant R is just a constant. I know the temperature. So volume is what I want to figure out, right? The V is our unknown. And I can figure out N from the 1 gram of KClO3 using the stoichiometry of the balanced reaction. So let's figure out N first. Figure out N, and then from N, I can use the ideal gas law to get V. So I have 1 gram of KClO3. If I figure out the molecular weight of KClO3 using the periodic table, that's 122.5 grams per mole. So I'm going to multiply by the reciprocal of the molecular weight to get rid of those grams and convert to moles. Now I want to look at the balanced chemical equation. For every 2 moles of KClO3, I'm producing 3 moles of oxygen gas. So I can use that mole ratio to convert to moles of oxygen gas, that 3:2 mole ratio. So if I do all of that, I have figured out my N. And of course, N is the number of moles of the gas that's produced. Okay, remember, ideal gas law only applies to gas. I can't use it for solids or liquids. Okay, so this is 0.0122 moles of oxygen gas. Now I can rearrange the ideal gas law to solve for volume because now I have moles of gas I can plug in for N. So 0.0122 moles of gas times the gas constant R, 0.08206 liter atmospheres per mole Kelvin, times the temperature. And the temperature here in Kelvin is going to be 20 plus 273, so that's 293 Kelvin. 293 Kelvin. Now I need to put the pressure in atmospheres. And I was given the pressure in torr. So remember that 1 atmosphere equals 760 torr. So if I want to convert the 750 torr to atmospheres, I need to divide by 760. So I'm going to say 750 divided by 760. So 750 torr, and this is 760 torr per atmospheres. That's going to give me the pressure in atmospheres. Okay, I just kind of did the unit conversion in that denominator. So that gives me a volume equal to 0.297 liters of oxygen gas. So now I suggest you go back through and make sure that you understand and can do all of these problems pertaining to the ideal gas law.